Let's talk a little bit about pulmonary gas exchange. Gases move between the alveolar air and the blood by passive diffusion down its pressure gradient. According to Fick's law, flow depends on two variables. There is a constant in there, but it depends on the pressure driving oxygen from one side to the other, or CO2 in the opposite direction, and it's inversely related to resistance. So if I increase the resistance, I decrease the flow. If I increase the pressure gradient, I increase the flow. Normally it takes about 3/4 of a second for blood to pass through the capillaries of the alveoli, and that blood reaches equilibrium in about 1/4 of a second. There is no diffusion limitation here. Diffusion is fine. If alveolar PO2, however, is very low, if blood flow is high, or if diffusion resistance is high, we may not reach equilibrium. That is, the capillary PO2 may not reach equilibrium with the alveolar PO2. And now I'm going to talk a little bit about diffusion and flow limitations. To do that, I'm going to use an example of trucks being filled by, it could be a grain silo or salt being loaded into trucks or sand. In this example, the truck is full. It's underneath the silo here, or the filling unit, and the truck that's ready to come in is too far away. This process must stop while this truck moves out of the way and wait for the next truck to come in. So there's a limitation of flow. The flow of trucks coming in to the filling point is too slow to keep up with the process here. So we have to stop filling and wait for the next truck to come in. So we have a flow limitation. In this example, the trucks are coming through at a normal speed. This truck is getting ready to come in, but there's a restriction here. This particular chute has a greater restriction, so it's filling slower. As a result, this truck has got to leave in order to allow this truck to come in before it's full. So before this truck gets full, it has to get out of the way for the next truck to come in. So this is a diffusion limitation. The trucks can't carry away as much as they normally would be able to if they could fill up, because there is a limitation to how fast the grain or sand or salt is coming out of this funnel. Now in this last example, the filling is exactly the same as up here in the top one. This is normal diffusion, but the trucks are coming through very fast. So these trucks have got to get out of the way to allow these trucks to come in, so to avoid a backup. So these trucks are not able to fill. They've got to get out of the way for the next truck to come in. So even though diffusion looks normal here, the trucks are moving in too fast, so we'd say that there's still a diffusion limitation. Diffusion would have to actually be much faster than normal in order to keep up with the rate at which trucks are coming in. In these two examples, we have a limitation that's based on diffusion. In this example, the trucks just aren't coming through fast enough. As a result, we have to stop filling in order to wait for the next one. Let's look at how this affects the lung now. Here we're looking at the systemic venous blood, which is also pulmonary arterial blood. PO2 is about 40 millimeters of mercury. And just as it enters the capillaries here, it quickly picks up oxygen from the alveolar air and reaches saturation about 1/4 of the way through. If this time represents our normal 3/4 of a second, this is about 1/4 of a second, and we've reached saturation at this point. We call this flow limitation because this blood is moving through the capillary and it's not able to pull out any more oxygen out of the air. It's already fully saturated. So there's a limitation to how much oxygen we can get out of the air because at normal speed the blood is moving too slowly. Now here we have a diffusion limitation. We're not able to reach equilibrium. The blood has not picked up as much as it could. This could be because of a high diffusion resistance. Now that high diffusion resistance could be, for example, pulmonary fibrosis, something that is causing the alveoli and the capillaries to spread apart, increasing the distance and therefore increasing the time required to reach equilibrium. So that could be a diffusion limitation. That would be similar to the second panel in the truck analogy. Blood could also be moving way too fast. This blood could be moving too fast. It could be, say, during exercise, we get the blood flow up very high, so it's getting through the capillary in less than 1/4 of a second. If it passes through the capillary in less than 1/4 of a second, and it takes 1/4 of a second to reach equilibrium, then it's not going to reach equilibrium. And that could be, for example, during exercise, we could reach a point where the blood coming out of the capillaries has not reached equilibrium. And that would be similar to the third panel on the truck analogy. There's one more instance that I want to bring up, and that is high altitude. In this example, I've got the alveolar PO2 at 60 millimeters of mercury. Venous PO2, or pulmonary arterial PO2, is now down around 20 millimeters of mercury. And even though blood flow is normal, it takes a longer time to reach equilibrium, and in fact may not reach equilibrium. We have a diffusion limitation. Now, why is this a diffusion limitation? The blood coming in is so unsaturated that it continues to pull oxygen out of solution. As oxygen moves into solution from the alveoli, the hemoglobin keeps pulling it out of solution. So more oxygen moves in, the hemoglobin pulls it out, continues, and by the time we reach the end here, the hemoglobin has not allowed the PO2 to reach equilibrium with the alveolar air. In addition, the pressure in the alveolar air is lower, so the driving force moving oxygen into blood has also decreased. So we say this is an apparent increase in solubility. As solubility increases, it takes a longer time for oxygen to diffuse and reach equilibrium with the air. One last thing I wanted to mention is carbon monoxide. Carbon monoxide is so soluble that it's extremely diffusion limited. I mentioned in an earlier talk on oxygen transport that carbon monoxide binds to hemoglobin approximately 250 times more strongly than oxygen. It's quickly binding to the hemoglobin, and carbon monoxide has a very difficult time reaching equilibrium with the alveolar CO concentration because hemoglobin keeps removing it from solution. So that's the difference between flow and diffusion limitations. And now I'm going to open up the pulmonary diffusion simulation and we'll do some experiments. This model, I'm showing a graph here of time along the capillary, 0 and under normal circumstances with this blood flow here at about 3/4 of a second to reach the other end of the capillary. And on this axis I'm looking at capillary PO2. And I'm showing the alveolar capillary PO2 here, about 40 millimeters of mercury, and the time along the axis. Now if I drag this little triangle here above the capillary, it will cause that little yellow ball to move, and we can see at this point we're at 98% saturation, and we're only about 0.13 seconds through the capillary. And I can continue moving this. So you can see we're 100% saturated. So at about 1/4 of a second, we are at approximately 100% saturated, 99.9% saturated. So 1/3 of the way through the capillary, we've reached virtually full saturation. The rest of the way along this capillary, the blood is no longer able to pull oxygen out of the alveoli. So we have this flow limitation. Blood is flowing too slowly to pull more oxygen out of the alveolar air. I can also alter alveolar PO2 down here to about 40 millimeters of mercury and about 100 at sea level. And I can change blood flow, I can change hemoglobin concentration, and I can change hemoglobin affinity. What would happen if you are polycythemic? Would we actually reach equilibrium later or earlier than normal if we were polycythemic? And I'll put us all the way up to 25 grams of hemoglobin per 100 milliliters of blood. So give it a thought. You can even pause if you want to take some time and think about it. Let's move it up and see what happened. It actually takes longer to reach equilibrium when you're polycythemic than normal. And the reason is there's more hemoglobin. As we add oxygen to solution, that extra hemoglobin starts taking it out of solution, keeping the PO2 low until all of the hemoglobin is saturated. The opposite would happen if we are anemic, and I'll go all the way down to 5 grams of hemoglobin. In this case here, very anemic. Also notice what happened here. The venous PO2, the pulmonary arterial PO2, is much, much lower now. And I'll talk about the arterial-venous O2 difference in another segment. And of course, if we're polycythemic, we're up to nearly 50 millimeters of mercury pressure. So let's go back to our initial condition. Let's increase the blood flow. So let's bring this up to 25 liters per minute. This would be a very fit individual. Most of us could not reach 25, but a very fit athlete could. Now it took only 0.15 seconds to make it through the capillary. It takes 0.25 seconds to reach equilibrium under normal sea level atmospheric conditions, so we really didn't reach equilibrium here, and we can move this triangle along till we reach the end. The PO2 is 99 millimeters of mercury, but not 100 millimeters of mercury. Let's try one more thing. Let's go to altitude. I'll bring this to 60. Well, let's bring it down to 40. Let's go way down. 40 millimeters of mercury pressure. Look at how long it took to reach equilibrium. It did reach equilibrium under these conditions. But look how long it took. It's almost out of the capillary before it reached equilibrium. And that is because the very low pulmonary arterial PO2 means that we've got a lot of unsaturated blood, which is pulling oxygen out of solution. As we're putting it in, the hemoglobin's pulling it out, and we have a very low driving force. The pressure trying to drive oxygen in has decreased. The pressure gradient is now between 40 and 24. So there's only a 16 millimeter mercury pressure gradient. So it takes longer to fill up. Go back to 100 millimeters of mercury of pressure, and now the pressure gradient is 60 millimeters of mercury difference. So there's a bigger force trying to drive oxygen into solution. Let's change the hemoglobin affinity. I'll increase the hemoglobin affinity for oxygen. Will that increase or decrease the time to reach equilibrium? If I increase the affinity for hemoglobin, think about that. Will it increase the time for the blood to reach equilibrium with the air, or will it decrease the time? And again, you can pause if you want to think about it, but I'm going to move on. It decreased the time. High affinity hemoglobin allows us to reach equilibrium faster because it takes oxygen out of solution faster, thereby decreasing the time to reach saturation. And the opposite, of course, will happen. Let's decrease affinity. And we can see now with low affinity, it's taking longer. And we'll go back to the original conditions. And just quickly, we could switch to oxygen content, and we can see the increase from about 15 volumes percent, milliliters of oxygen per 100 milliliters of blood, and here we're at 20% given this PO2. And down here we can see dissolved oxygen, very little dissolved oxygen. Well, that concludes this talk on pulmonary gas exchange, on diffusion and flow limitations.